My name is Martin and I will be presenting the work extracting Taint specifications for JavaScript libraries, which is joint work with Chris, Max, Anders, and Michael. So let's begin by considering the NPM system for JavaScript. The NPM system contains more than 1 million packages. There are more than 1 billion package installations taking place every day, but more alarmingly, there are at least 1,400 known security vulnerabilities in these packages. One of the most common types of vulnerabilities we see in practice is injection vulnerabilities. In an injection attack, a malicious user of a system intentionally crafts an input to the system that causes the system to diverge from its intended behavior. We say that there is an injection vulnerability whenever data can flow from an untrusted source to a trusted sink and no sanitization or validation of the data takes place on the way. For example, if data from an HTTP request flows into a call to eval, then a malicious user could potentially cause arbitrary code execution on the system. There is a dual problem where data instead leaks from a trusted source to an untrusted sink, which we also address in the paper. But due to the time constraints of this talk, I will focus only on the former problem. The usual solution for detecting injection vulnerabilities is to use a taint analysis. A taint analysis finds injection vulnerabilities by looking for data flow between untrusted sources and trusted sinks. A static taint analysis is often preferred because it's fully automatic and potentially sound, meaning that it will detect all injection vulnerabilities. But due to the reflective and dynamic nature of JavaScript programs, static taint analyses don't scale well for large JavaScript programs. However, a typical JavaScript application is just a set of modules, where most of the modules are provided by third-party libraries. So we can achieve scalability by analyzing each module in isolation using a modular analysis. For example, the LDGM analysis. Because the module that is being analyzed may interact with other modules, it is necessary to supply handwritten summaries of how taint flows through these modules. Writing summaries is both time-consuming and error-prone, and if summaries are missing or incorrect, the analysis may report false negatives. In this work, we propose a solution. We use a dynamic analysis to automatically generate the summaries. Our approach is fully automatic. The inferred summaries are very precise, and summaries from multiple runs can be combined to one general summary. To understand our approach, let's consider this example that contains an injection vulnerability. The user input variable gets its object value from a user-supplied HTTP header. The foreign method iterates through all of the property values of the user input object. For each iteration, the property value is passed to the callback as the value parameter, as indicated by the dotted arrow. The value is then passed to the rimref function. Rimref takes a path and a callback and deletes the file or directory of the path. The getHeader method is a taint source, since it reads a header value of an HTTP request that comes from the user. And the first parameter of rimref is a taint sink, since the value flows into a file system API method for deleting a file or a directory. Therefore, the user can delete arbitrary files on the system by carefully crafting the HTTP request. So this example uses two methods that come from external libraries: the foreign method from the Lodash library and the rimref function from the rimref library. For a modular taint analysis to detect this vulnerability, it requires two pieces of information about these external modules. First, it has to know that the property values of user input flows into the value parameter of the callback function. A novel concept known as a propagation summary is used to encode facts like this. The flow between user input and value is encoded by this propagation summary. It consists of two access paths, and it says that all of the properties of the first parameter of the foreign method on the Lodash module flows into the first parameter of the callback supplied as the second parameter to the foreign method on Lodash. The second piece of information required is that the first parameter of rimref flows into a sink. That fact is encoded by this access path. So let's consider how an analysis may infer this propagation summary and the additional sink. There are two places in the code where values flow from the client into the library, as illustrated by the blue boxes. We call those places library entry points. There are three places where values flow from the library into the client. We call those places library exit points. Notice the parameter of foreign's callback comes from the library, but the callback itself is in client code, so the parameter is considered a library exit point. To infer Taint summaries, we use the dynamic analysis Taser. Taser monitors the execution of test suites and records the interactions taking place between the modules to infer propagation summaries and additional things. To generate better summaries, Taser is run with many different test suites. All of the inferred summaries are eventually combined to one general summary. Once a summary is generated, it can be reused across many runs of the static analysis. As illustrated by the figure on this slide, Taser uses a technique known as a membrane to keep track of the boundary between client and library code. The membrane grows dynamically as the analysis is running. Whenever a value passes the membrane, it too becomes part of it. For example, a callback function passed to the library becomes part of the membrane, such that the passing of the boundary that takes place once the callback is called can be tracked. Each point of a membrane is assigned an access path, representing its location in the library API. These access paths are used when new propagation summaries and additional things are added. Taser infers the propagation summaries by tracking how values flow between library entry points and library exit points, as illustrated by the path on this figure. The analysis also tracks how values flow between library entry points and existing things, also as illustrated by the highlighted path. Such a flow results in an additional sink being added to the summary. To evaluate the technique, we ran Taser on 3/3 of the top 1000 NPM packages, including the test suites of up to 200 clients of each package. Taser managed to extract almost 8,000 propagation summaries and 146 additional sinks, using on average 112 seconds per client. By plugging the results from Taser into the existing static analysis LGGM was able to find 136 new injection vulnerabilities. Manual examination of 30 of the new alarms showed only 6 of them are false positives, and that all of the false positives are due to imprecision in the static analysis. So in conclusion, we present a novel technique for inferring Taint summaries for JavaScript libraries. The Taser analysis monitors the data flow between client and library code during the execution of existing test suites. Based on this flow, precise Taint summaries are constructed using an access path mechanism for identifying library entry and exit points. So furthermore, we show that with the Taser inferred summaries, an existing state-of-the-art static Taint analysis can find previously unknown injection vulnerabilities.